Hi everybody, buongiorno, buon pomeriggio. Thank you for the invitation. That's a pity that I couldn't make it, but I really appreciate the possibility to give this presentation online. So what I want to discuss today is the kind of progress and the perspective that we are seeing concerning the use of van der Waals heterostructure to elaborate spintronic application. And first of all, I like to mention that part of my presentation is inspired by a very recent review articles that we are publishing in Nature Nanotechnology with Sierra, Fabian, Kawakami, and Valenzuela. So at the time of the workshop, Transient Magnetism, this paper will have been fully published. So why are we interested in graphene and van der Waals heterostructure? Everything started almost 10 years ago when the graphene flagship project was selected by European Commission and launched. In its mission, it was clear that these two-dimensional materials could present very interesting perspective for spintronics. So that was one of the direction of investigation. And what made graphene so attractive at the time was this material is just based on carbon, and sp2 configuration was anticipated to be an extremely good conductor of spin information, given its low spin orbit interaction and very large mobility. Many years later now, we have the conviction that indeed this materials offers unique perspective for transferring spin information over unprecedented scale. And this is a result published by IMEC and ICN2, in which they show that at room temperature, you can achieve very long spin diffusion lengths or spin lifetime and spin lifetime in a scalable graphene, a graphene that you can grow with catalytic vapor deposition, CVD, so which make the system very useful for application because it's integrable. Also, let me say that it's not very necessary to achieve a huge mobility to reach those numbers that are enough for designing active spin device. Essentially because, as we could show theoretically, the spin diffusion lengths does not really depend on the sources of scattering or the strength of scattering, because in these polycrystalline morphologies, it turns out that it is just related to the spin orbit coupling strength that is induced by the substrate on which graphene is deposited. And CVD graphene is one of the most important materials now for wealth application beyond spintronic, as you can see here in this plot several illustration of groups and institutions that are working with CVD from graphene in real application. What is also very promising is the fact that the European Commission, together with Graphene Flagship, have launched the so-called experimental pipeline. And this is really important because you really need to have this large volume production of functional electronic devices based on these two-dimensional materials, but you need the proper infrastructure to develop this kind of architectures and devices. So there is now an important effort that has been initiated and hopefully will be maintained in the next 10 years, because there is still a long way to go in order to come to very efficient commercial products but a foundry is necessary to move towards this objective. And particularly now, thanks to the large-scale graphene, you can engineer very complex architecture. You can deposit a lot of different type of contacts, and you can probe the spin information propagation over very long distance through very different type of interconnected devices. So the Graphene flagship also put in places a European task force to explore the full capability of these materials for spintronic application. And since then, we've been very active in demonstrating the potential of graphene and two-dimensional material and van der Waals structure for concrete spintronic application. We elaborate a roadmap in 2015 that we have followed quite regularly. And let's say one of the major aspects and the most interesting property of graphene is that not only it can transfer information over unprecedented scale at room temperature in scalable materials, but also it can be controlled by very weak proximity effect. And using a lot of different type of van der Waals heterostructures, we can achieve very interesting active spin device. This is a theoretical work, which was one of the first to demonstrate that graphene can become magnetic when you deposit it on a magnetic insulator, such as YIG, in which the exchange coupling for a super clean interface was predicted to be gigantic. And as a result, a very sizable band gap could be open and spin splitting of the band structure. Just a couple of days, or let's say a week ago, Bava and this group have evidenced that you can use graphene interface with two-dimensional antiferromagnets, and that you can probe this type of proximity, giant proximity effect. And in their work, where they measure modification of the Hanley spin position signal, they could estimate that the achieved exchange coupling was in the order of 170 Tesla. So we have a lot of possibilities in order to design this type of van der Waals heterostructure with a functionality for spintronic. And but what I want to point out is the perspective for spintronic application in the field of non-volatile memory. Early on, the group of MAGNETISM in Grenoble, together with colleagues at CNRS, demonstrated that when you coat magnetic materials with graphene, you have a very important gain beyond preserving the property of the interface, avoiding oxidation. You will also increase considerably the PMA, the perpendicular magnetic anisotropy. And this is an important figure of merit for STT-MRAM technologies. More recently, together with a more international consortium, including a big company like Samsung or Global Foundries, we have set up a new roadmap for the next 10 years to come, in which we discuss all the aspects that current technology are facing with that could be solved by a proper integration of two-dimensional materials. And this in the perspective of STT-MRAM, but also spin orbit torque-based non-volatile memories. So let me come closer to a more concrete illustration and discussion about the gain of this type of materials and heterostructure for designing active spintronic devices. And I will mainly point out the generation of pure spin current through the spin Hall effect, and its relation to the spin orbit torque mechanism. So spin Hall effect, as I am sure everybody knows in this audience, is the possibility to create pure spin current by an electric current when you use a strong spin orbit coupling materials. Especially in this van der Waals heterostructure, one of the first interesting case was to enhance spin orbit coupling in graphene, for instance, by depositing this transition metallic alkogenide in order to locally separate the spin population and having this transversal spin current. So one question was, what could be the figure of merit of this mechanism? And in order to measure that, usually we use this spin Hall current, which somehow tells you how much spin current you can create for a given charge current. So there is a very important aspect here, because all conventional materials, let's say that the ones that have been reviewed here, and especially heavy metals, have been facing a lot of problems in order to respond to the demand of spintronic application. And the problem is the following, that usually you would like to optimize both the spin diffusion lengths and the capability you have to modulate the spin during the propagation. And the propagation can be very efficient, very long, but at the same moment, locally, you want to rotate the spin and make some kind of device, spin valves, and so on and so forth. But usually when you increase the spin orbit coupling in this type of materials, you might find the augmentation of the spin Hall angle, but generally you also reduce the spin lifetime and the spin diffusion length, and vice versa. So that makes this type of material, so if you look at the correspondence, what you would like to achieve is really to come in this upper right part of the graph, where you maximize both of them. And one important point here is to keep in mind the fact that with these conventional materials, the product of spin lifetime times the spin Hall current is in the order of 0.1 nanometers. So the absolute value of this product doesn't mean really anything. What is important is that maximizing both quantity means to enhance this number. So one of the questions we addressed and we answered was how this type of interfacing could indeed bring an enhancement of spin properties and overcome the limitation of the previous materials and the previous rule I've just mentioned before. So to investigate this, we first studied theoretically the capability of this type of interfaces to generate large spin Hall currents. We are very lucky in the sense that when you interface graphene with a lot of different materials, as we have reviewed now in the paper here, you can have a very realistic description of the impact of this proximity effect, not only on the bond structure, but also on the spin texture of the state. And the spin texture of the states will be fundamental to understand the resulting spin transport properties. So we have, in addition, based on a lot of calculation from first principle, realized that you can have a minimum set of effective Hamiltonian that will capture all the possible type of interfacing you're interested with, especially including these new 2D magnets or the strong spin orbit coupling materials. So then, based on this description of this effective Hamiltonian, we can investigate, compute exactly the spin Hall angle, for instance, using this ratio of the spin Hall conductivity over the dissipative conductivity. So